Hello students, welcome to another lecture. Here we will study about isomerism, which is one of the important property of organic compound. So first we see here about the isomers. Here for one of the organic compound having its molecular formula C3H6O. And the molecular formula means the total number of atoms which are present in this structure is called as molecular formula. And this molecular formula is represented by the splitting of this carbon, hydrogen and oxygen is called as the structural formula. So this molecular formula is represented by CH3 C double bond OCH3 is the structural formula for acetone. And one of the possible structure for this molecular formula is CH3CH2 C double bond OH. Now see, the molecular formula is same for these two structures, but they show the different structural formula. So these two structures are called as isomers of each other. The first three alkane or the members from the alkane family, methane, ethane, propane, they are represented by only one structural formula. As they contain less number of carbon atom, there is no more possible structure for the ethane. It shows only one structure, CH3CH3. For propane also. But the alkanes containing 4 or more carbon atom, they are represented by more than one structural formula. Here for the butane, which having the molecular formula C4H10, it is represented by the following two formulae. One is the N-butane. Here all these carbon atoms are in a straight chain, and in this structure one of the CH3 group is on the straight chain. So this is considered as a branched group. So its name is 2-methyl propane, or what we can say isobutane. So butane having the same molecular formula C4H10, but it shows the two different structure. So this is called as the isomerism. Means the compound having same molecular formula but different structural formulae are called as isomers of each other, and this phenomenon is called as isomerism. Even though isomers have same molecular formula, the atoms are linked in different manner, resulting in a different structure. And these isomers have different physical and chemical properties. So this is the definition for isomerism. Mainly isomers are classified into two types: structural isomerism and stereoisomerism. And further, these structural isomerisms are classified into chain isomerism, position, functional, metamerism, and tautomerism. Whereas in the stereoisomers, they are classified into geometrical isomerism and optical isomerism. So first we see about the chain isomerism. Now see, for the chain isomerism, these isomerisms are due to the change in the structure of chain. The molecular formula for pentane is C5H12, and it is represented by this different structure. One is the normal pentane and pentane. These 5 carbon atoms are in chain. This is isopentane. One methyl group is on the straight chain. Here for the neopentane, on one carbon atom, 4 methyl groups are present. So all they having the same molecular formula C5H12, but they are represented in the different structure due to the change in their chain. Okay, one is a straight chain, one is the branch. Here single methyl group is in the branch. Here two methyl groups are branched. So these are called as chain isomers of each other. One more example for the butanol. Here one butanol which having the formula C4 and with this OH group, hydroxy group. So here one methyl group is on the branch of these 3 carbon atom with the OH group. So 2 methyl, 1 propanol and 1 butanol having the same molecular formula but the different structure due to the change in their chain, and therefore these are also chain isomers of each other. For the hexane, C6H14, and now see, these are the different examples for the chain isomers of hexane. This is straight chain, and all these are the branch where methyl groups are present on these carbon chain, and they form the different structure: 2-methyl pentane, 3-methyl pentane, 2,2-dimethyl butane, 2,3-dimethyl butane. So these are the different isomers of hexane, and all these are the bond line structure for the isomers of hexane. See here these two structure, cyclobutane and methyl cyclopropane, means one side chain is present on the ring, means one is the open chain and the other one is the cyclic compounds. So they having the same molecular formula but the different structure, one is the open chain and one is the cyclic chain. So these are called as ring chain isomers. We see one more example here. See propene, CH3 CH double bond CH2, and cyclopropane. They are having the same formula. They contain the same number of carbon, 3 carbon and 6 hydrogens. So or they differ in their only structure. One is the open chain and one is the closed chain. These are called as the ring and open chain isomers. Propine and cyclopropene, having the same number of carbon atoms, see, both the contain 3 carbon and 4 hydrogens. This is for the position isomers. Positional isomers are constitutional isomers that have the same carbon skeleton and same functional group, but they differ from each other in the location of functional group. Or they show the position of functional group on the different carbon atom. See the first structure, propyl chloride, both having the same molecular formula. They both the contain 3 carbon, 7 hydrogens and 1 Cl. But what is the differ in their position of Cl? See here, the Cl is present on the first carbon atom, and therefore it is a propyl chloride, and here Cl is present on the second carbon atom, therefore isopropyl chloride. They are differ in their structure due to the position of Cl. This is on the first carbon atom, this is on the second carbon atom, and therefore these two are the positional isomers of each other. 1-butene and 2-butene. These two are positional isomers due to the change in the position of double bond. Here both having the same number of carbon and hydrogen, but they differ in the position of double bond. Here bond is present in between carbon number 1 and 2. Here bond is present in carbon number 2 and 3, and therefore it is 1-butene, 2-butene, having the same molecular formula but different in the position of double bond. Similarly, 1-pentene, 2-pentene. Okay, the position of double bond here in between carbon number 1 and 2, here 2 and 3. Now see these two structures, they show the same type of change here. These both having the same number of branching here, but what they having the difference here, this is the structure for 2-methyl 1-butene, and this is for the 2-methyl but2-ene, and these two are functional isomers or positional isomers of each other as they having the different position of double bond. These are also examples for the positional isomers as due to the presence of Br. Here Br is present on this carbon atom 1-bromobutane. This is 1-bromo-2-methyl propane. The Br is present on the first carbon atom but the remaining structure is branched. Here this is a tertiary bromide structures, tertiary butyl bromide or 2-bromo-2-methyl propane. So all they having the different structure due to the position of Br, and therefore these are positional isomers of each other. You can also get the positional isomers on benzene ring. Consider the molecular formula C6H4Cl2. And here the different isomers depending upon the position of chlorine atom. Here chlorine is present on the carbon number 1 and 2, 1,2-dichlorobenzene, 1,3-dichlorobenzene, 1,4-dichlorobenzene. Means these are the different forms of ortho, meta and para-dichlorobenzene. So these are positional isomers of each other due to that they are differ in their position of functional group Cl. These are the now see the functional group isomers. Third type we completed about the chain isomerism and positional isomers. This is about the functional isomers. Molecule with the same molecular formula but with atoms are arranged to give the different functional group in space. Means see the molecular formula C2H6O. and it shows the two different structure. One is CH3 CH2OH and one is a CH3OCH3, both having the same molecular formula, carbon number 2, hydrogen 6 and 1 oxygen. But here it shows the functional group OH, the hydroxy as a functional group. Here it shows ether as a functional group. These two alkyl groups are bonded with the oxygen, therefore they form the ether functional group. Means due to the change in their structure, they form different functional group, and therefore these are functional group isomers of each other. See example, ethanol and methoxymethane having the same molecular formula but different structure. One is the alcohol, one is the ether. One more example, see acetone and propanol. These are the functional isomers having the same molecular formula C3H6O. But one it forms the ketone functional group, whereas here propanol it forms aldehyde as a functional group. C double bond O is bonded with the two alkyl group. Here C double bond O is bonded with the one side carbon, one side hydrogen. And therefore aldehydes and ketones having the same formula C3H6O but differ in their functional group, and therefore these two are functional isomers of each other. Some more examples. Here now see, only the change is here. Hydrogen is present here at the terminal and here Cl is present. Okay, means C double bond O is bonded to the one side, carbon is same here, but only change is to the other side. It form acyl chloride functional group, C double bond OCl. Here it form aldehyde as a functional group. Or we see here these two example. OH group is present directly on the benzene ring and CH3 here. So this is the example for the phenol, 3-methyl phenol. Here OH group is present on the CH2 and the CH2 is present on the benzene ring. Therefore benzyl alcohol, it forms the functional group alcohol, and this is for the functional group phenol. So 3-methyl phenol and benzyl phenols, these two are functional isomers of each other. And see here, all these examples are for the same molecular formula C4H8O, these three examples. Okay, butanol, butanone or isobutyraldehyde. All they having the same molecular formula but different in their functional group. These two, this is for the aldehyde. This is also for aldehyde, but they show the structure different. Here, this is which contain the ketone as a functional group. So butanone and butanol are functional isomers of each other, or butanone and 2-methyl propanol or isobutyraldehyde are functional group isomers of each other. Nitrite and nitro here are NO2, both having the same formula RNO2, but see here bonding is here between the alkyl group and oxygen. Here R is with the N of NO2 group. So nitrite and nitro, these are also functional isomers of each other. Or here one more example, methyl cyanide, methyl isocyanide. We have studied all these functional group. Okay, in the functional group examples, cyanides, isocyanides, nitro, nitrite. So methyl cyanide or methyl isocyanide, these two are functional group isomers of each other. Now next isomer type is metamerism. This type of isomerism arises due to the unequal distribution of carbon atom on either side of the functional group. In other words, when the different alkyl groups are attached to a functional group in a compound, they show the metamerism. See here example, CH3, CH2O, CH2, CH3. It shows the oxygen, and these two different alkyl groups are attached to the functional group. Here one more is the CH3O, CH2, CH2, CH3. Means all they having the same number of carbon. See carbon 1, 2, 3, 4. Carbon 4, hydrogen 3, and these two 5. And these 2 and 5 means 10. They contain 4 carbon, hydrogen 10 and with 1 oxygen. See here 4 also 3 hydrogen, here 3, 3 and 1 means 10 hydrogen, 4 carbon and with 1 oxygen. But they show the different alkyl group are attached with the functional group ether. Here one methyl group, here propyl. Here isopropyl group is present, here methyl group is present. So these are called as metamers of each others. means here diethyl ether, and this is the methoxypropane. These two are metamers of each other. These are the example: methoxypentane, ethoxybutane, and propoxypropane. These are metamers of each other. Now here these two structures, they have the same structure, but what is they are differ in the position of these O. Okay, they are present at the adjacent and they are completely opposite to each other. So these are the ortho position. This is the para. So orthodioxine and paradioxine, these two are metamers of each other. Next isomer type is tautomerism. Tautomerism is a special kind of functional isomerism. In this case, two isomers are in a stable dynamic equilibrium and they can alter their structure depending upon their needs. Now see here these two structure. One is the ketone CH3 C double bond O CH3, a keto form of acetone. Okay, and here this keto means C double bond O is present here, carbonyl too, and in this structure the bond is shifted here in between these two carbon atoms and it forms the double bond in between the two carbon. Therefore it is a alkene, and due to that H is form the bond with that oxygen and therefore it form OH group, and therefore this form is called as enol form. Enol due to the presence of double bond and OL due to the presence of OH group. So this is the enol form of acetone. So now see what they are only differ in the one atom is only position of the one atom is only differ here. It is with the CH3 and whereas in this it is with the H. So these two are called as tautomers of each other. Means these two are in the stable dynamic equilibrium positions and they shows the change in their structure depending upon their need. These two are also tautomerisms forms, tautomers of each other. So what we can see here for this tautomerism, this is a phenomenon in which two structural isomers differ in the relative position of their atoms and spontaneously interconvertible and can exist in dynamic equilibrium. And these two forms are called as tautomeric equilibrium, or the phenomenon is called as tautomerism. So here this is for the NO2 group, CN double bond O, and this is the oxygen which is a negatively charged. So one hydrogen here which is bonded with this carbon, that hydrogen it form the bond with this oxygen, and due to that double bond in between the carbon and nitrogen. So here the bond is present in between the nitrogen and oxygen, in this structure in between the carbon and nitrogen. So these two forms are tautomers of each other. Next type of isomerism, this is the stereoisomerism, one important branch of isomerism. So stereoisomerism is a form of isomerism in which molecules have same molecular formula and sequence of the bonded atom. Means they are having the same molecular formula and sequence of bonded atom but differ in the three-dimensional orientation of their atoms in space. So there are two types of stereoisomerism: geometrical isomerism and optical isomerism. First we see about the geometrical isomerism. The isomerism which is due to the difference in spatial arrangement of atoms or groups of atoms is called as geometrical isomerism. And this is isomerism is due to restricted rotation of about the carbon-carbon double bond. See these two structures, carbon-carbon double bond is present here, but what these two structures are differ in there. Now see here these CH3 groups are present to the one side of double bond, and here this CH3 and CH3 are group present opposite to that of the double bond. When these two similar groups, you can see here CH3 or HH, when the similar group are present to the one side of double bond, this is called as cis structure. And as these four carbon atom bond is present 2 and 3, therefore cis but 2 Ne. In this structure CH3 are present to the opposite side of double bond. This structure is called as trans. So trans but 2 Ne. So cis and trans, these are geometrical isomerisms of but 2 Ne. Some more examples here. See, 1,2-dichloroethene. These two chlorine are present to the opposite side of double bond. This is a structure for the trans, and here the similar group are present to the one side of double bond, structure for the cis. So this is for the 1,2-dichloroethene. One more example, 3-hexene. Here the similar group CH2, CH3, ethyl group are present to the one side. Here these two are to the opposite side. Therefore, hex 3-Ne, 1,2-dichloroethene or 2-butene, they show the cis and trans structure depending upon the position of similar group to the one side of double bond or to the opposite side of the double bond. This is called as the geometrical isomerism. Here for in this structure, similar groups are present at the adjacent position in this structure. So these are also called as cis isomers. Here Br, NH3 and NH3. Similar group are present to the opposite side of this platinum. This is a coordination complex compound where the platinum is surrounded by these four groups, and these two groups they form the planar geometry, and when these two groups are to the opposite position it form the trans isomer, and here NH3 are to the adjacent position it form the cis isomer. So this is about the geometrical isomerism. For optical isomerism, the optical isomers are the two compounds which contain the same number and same kind of atom and bonds, but the connectivity between the atom is same, but what they show the different spatial arrangement of atoms. Means connectivity of these between the atom is same, but they show the spatial arrangement is different, and therefore these are non-superimposable mirror images of each other, and such type of structures we call here optical isomerism. Example for the optical isomerism, see this is the important example for the optical isomerism, carbon which having the four different groups COOH, CH3, OH and H. And here it shows it one more structure here where see the CH3 group is present towards here to the left side, here to the right side, and these two different forms are the lactic acid. One it is called as the dextrorotatory, one is called as the levorotatory, and these two are called as optical isomers of each other. Means what we can say that see here the mirror images are same here, but when we put on each other these two forms they show the different structure, and therefore this such type of structure are called as the optical isomerism. 2-chlorobutane, it also shows the optical isomerisms. Mainly the carbon, which is the asymmetric carbon atom, they shows the optical isomerism. Asymmetric carbon atom means the carbon atom bonded with four different group or atom. It's called as asymmetric carbon atom. Carbon is bonded here with the ethyl group, one methyl, one chlorine and one hydrogen. And as it shows the four different group on each other, it shows the optical isomer. Here the Cl is present here to the right side, here Cl is present toward the left side. So this form is called as dextro form, this is called as the Leo, or what we can see here, this dextro and Leo form of 2-chlorobutanes are optical isomers of each other. So this optical isomerism is due to the this arrangement of these atoms or group is different, three-dimensional arrangement is different. So this is about the stereoisomerism, geometrical isomerism and optical isomerism. And this is all about the isomerism. Thank you.